Welcome to physics class. Good morning, everyone. My name is Gias Uddin. My dear students, today we are going to discuss about another important topic. This topic is numerical based on Devission Germer experiment. Numerical based on Devission Germer experiment. Okay. So this is our first numerical problem, and the statement of this problem like this: find out the glancing angle at which electrons of 100 volt should fall on the lattice plane of a crystal to obtain a strong Bragg's reflection in the first order lattice spacing, and D equal 2.15 angstrom. Okay. Solution. Solution. The given information of this question, given lattice spacing D equal 2.15 angstrom, and this is equal to 2.15 into 10 to the power minus 10 meter. Okay. And potential, accelerating potential B equal 100 volt, and particle is electron. This is clear that particle is electron. So mass of particle equal 9.1 into 10 to the power minus 31 kg, and charge of electron equal 1.6 into 10 to the power minus 19 coulomb. Okay. Find out the glancing angle. We know that glancing angle is denoted by theta. Theta equal what? Okay. Theta equal what? And falls on a lattice plane of a crystal to obtain the strong Bragg's law. Yes. So n equal first order n equal 1. So we are going to find out first of all lambda. So we know that we have lambda equal b, lambda equal 12.27 under root of b. Okay. The value of 12.27 and potential difference is equal to 100 volt, and 12.27 and root over 100, that means 10, and this is equal to 1.227 angstrom. 1.227 angstrom. So this is our required wavelength. Now we are going to find out glancing angle. Now we can apply Bragg's equation again. From Bragg's law, twice d sin theta equal n lambda, and theta equal sin inverse n lambda divided by twice d. Okay, n lambda divided by twice d, because we know that according to Bragg's law, twice d sin theta equal n lambda. This is called Bragg equation, and theta equal sin inverse n lambda divided by twice d. Okay. Now sin inverse and n, the value of n equal 1 and lambda equal 1.227 divided by 2 into d spacing distance. This is equal to d equal 2.15 angstrom. Okay, 2.15 angstrom. After solving this part, we will get 16.5 degree. So theta equal, our required glancing angle is theta equal 16.5 degree. For your better understanding, I am going to repeat it once again. The statement of this question: find out the glancing angle at which the electrons of 100 volts should fall on the lattice plane of a crystal to obtain a strong Bragg's reflection in the first order. Okay, and lattice spacing d equal 2.15 angstrom. So the given information of this question, this is lattice spacing and this is denoted by d. So d equal 2.15 angstrom. Okay, and angstrom we can convert it 2.15 into 10 to the minus 10 meter, because we know that 1 angstrom equal 10 to the power minus 10 meter. Okay, so this is our first given data. Second data is also B equal 100 volt. B equal 100 volt. This is called accelerated potential. So B equal 100 volt, and A particle is also electron, so its mass value of 9.1 into 10 to the power minus 31 kg, and charge value is also 1.6 into 10 to the minus 19 coulomb. And we have need to find out theta, that means glancing angle equal what, and n equal 1. This is first order. For first order, we can write n equal 1. First of all, we are going to find out lambda equal lambda. This is de Broglie wavelength in terms of potential difference. So we can write lambda equal 12.27 under root of b. This problem also we can solve another formula, lambda equal h by under root of 2m qb. But in shortly, we can solve this problem with the help of this formula. Okay. So when the value of b equal 100 volt, so after solving this part, we will get 1.227 angstrom. And again, from Bragg's law, we can write twice d sin theta equal n lambda. This is called Bragg's equation, and theta equal sin inverse n lambda divided by twice d. When all values substituted in this equation, then we will get the value or magnitude of the theta, that means glancing angle, is equal to 16.5 degree. Thank you. Okay, our next numerical problem is, the statement of the numerical problem is a beam of monoenergetic neutrons corresponding to 27 degrees Celsius is allowed to on a crystal. A first order reflection is observed at a glancing angle 30 degree. Calculate the interplanar spacing of the crystal. Okay. Now, solution of this question given. The information of this question, glancing angle is 30 degree, so theta equal 30 degree, and particle is Newton. This is clear that, so mass of Newton equal 1.67 into 10 to the power minus 27 kg. Okay. And a first order reflection, so integer number n equal 1. Okay. And Planck constant h equals 6.62 into 10 to the power minus 34 joule second. Okay. And k, this is called Boltzmann constant. So k equal 1.38 into 10 to the power minus 23 joule per Kelvin. Okay. And we need to find out interplanar spacing, that means d equal what. So we are going to find out lambda equal, we have, first of all, we are going to find out lambda, that means wavelength, lambda equal h by under root of 3m kt. Temperature, yes, temperature is 27 degrees Celsius. So T equal 27 degrees Celsius. And we know that Celsius is not SI unit of temperature. So it should be converted in SI system. So that's why 27 plus 273, and this is equal to 300 Kelvin. Okay. Now all the values put in this equation. H equals 6.62 into 10 to the power minus 34. Under root of 3 into m equal mass equal 1.67 into 10 to the power minus 27 into k is Boltzmann constant, so 1.38 into 10 to the power minus 23, and also temperature, the value of temperature equal 300 Kelvin. After solving this part, we will get 1.78, this is equal to 1.78 into 10 to the power minus 10 meter, and this is equal to 1.78 angstrom, because we know that 10 to the power minus 10 meter is equal to 1 angstrom. So this is our required wavelength. Now we are going to find out interplanar spacing. Okay. Again, we can apply Bragg's equation. From Bragg's equation, twice d sin theta equal n lambda. This is called Bragg's equation. Okay. We need to find out d equal, we can write n lambda divided by 2 sin theta. Okay. So the value of n equal 1 for first order, and lambda equal 1.78 into 10 to the power minus 10, and divided by 2 into sin 30 degree. It means that the value of sin 30 degree equal half. So 2 and 2 cancel to each other. Finally, we can write 1 into 1.78 into 10 to the power minus 10. After solving this part, we can write 1.78 into 10 to the power minus 10, and this is equal to 1.78 angstrom, because we know that 1 angstrom equal 10 to the power minus 10 meter. So this is our required interplaning space or distance, okay, and this is our required wavelength. For your better understanding, I am going to repeat it once again. The statement of this question like this: a beam of the monoenergetic neutrons corresponding to 27 degrees Celsius is allowed to on a crystal. A first order reflection is observed at a glancing angle 30 degree. Calculate the interplanar spacing of the crystal. So the given information of the question, theta, this is called glancing angle. So theta is also given, theta equal 30 degree, and particle is Newton. So the mass of the Newton particle is 1.67 into 10 to the minus 27 kg, and this is first order. So number n equal 1, and h is also Planck constant. This is equal to 6.62 into 10 to the minus 34 joule second, okay, and k is called Boltzmann constant, and its value is equal to 1.38 into 10 to the minus 23 joule per Kelvin, and T equal temperature, and temperature equal 27 degrees Celsius. We know that degree Celsius is not SI unit of the temperature. That's why it should be converted in SI system. So 27 plus 273, this is equal to 300 Kelvin. And D equal what? First of all, we are going to find out lambda equal h by, and this expression is called, this is the de Broglie wavelength, the expression of de Broglie wavelength in terms of temperature. So lambda equal h by under root of 3 mkt. When all the values substituted in this equation, then we will get lambda equal 1.78 angstrom. Okay. Again, we can apply from Bragg's equation 2d sin theta equal n lambda and d equal n lambda divided by 2 sin theta. When all values substituted in this equation, then d equal 1.78 into 10 to the minus 10, and this is equal to 1.78 angstrom. Okay. Okay. Our next numerical problem is this. Okay. The statement of this problem: a crystalline material has a set of a Bragg's planes separated by 1.1 angstrom for 2 electron volt neutrons. What will be the highest order Bragg's reflection? So the given information of this question, given 2 electron volt, this is energy. So we can write E equal E equal 2 electron volt, and we know that 1 electron volt equal 1.6 into 10 to the power minus 19 joule, because we know that 1 EB equal 1.6 into 10 to the power minus 19 joule. So we can write 2 electron volt equal 2 into 1.6 into 10 to the power minus 19 joule. After calculating, we get 3.2 into 10 to the power minus 19 joule. This is our first information. And a crystalline material has a set of a Bragg's planes separated by the 1.1 A. This is interplanar spacing. So we can write D equal 1.1 angstrom, and this is equal to 1.1 into 10 to the power minus 10 meter, because we know that angstrom is not SI unit of the distance. So that's why it should be converted in SI system. So 1.1 into 10 to the minus 10 meter. Okay. And particle is Newton. This is clear that particle is Newton. So mass of particle is m equal 1.67 into 10 to the power minus 27 kg. And also Planck constant h equal 6.62 into 10 to the power minus 34 joule second. And lambda, first of all, lambda equal what? Okay. What will be the highest order Bragg's reflection, and n equal what? Okay. First of all, we are going to find out wavelength. So lambda equal, we can apply de Broglie wave equation. Lambda equal, we have lambda equal h by under root of 2me. This is the expression of de Broglie wavelength in terms of energy. Now all the values put in this equation. Lambda equal the value of h 6.62 into 10 to the power minus 34, and under root of 2 into m, the value of m equal 1.67 into 10 to the minus 27, and energy is equal to 3.2 into 10 to the minus 19 joule. After solving this part, you will get the result is 0.202 into 10 to the power minus 10 meter, and 10 to the minus 10 meter is equal to 1 angstrom. So we can write finally 202 angstrom. So this is our required wavelength. Now we are going to find out what will be the highest order of the Bragg's reflection. Again we can apply Bragg's equation. Again from Bragg's equation 2d sin theta equal n lambda. So we can write n equal 2d sin theta divided by lambda. Okay. Now n equal 2d sin theta 2d sin theta divided by lambda, theta equal 90 degree, theta equal also 90 degree. Okay. So the value of d equal 1.1 into 10 to the minus 10, and sin 90 degree, we know that the value of sin 90 degree equal 1, and lambda equal this 0.202 into 10 to the power minus 10. After solving this part, we will get the value of n equal 10.89, and this is approximately equal to 10. So the required value of n equal 10. That means highest order is n equal 10. For your better understanding, I am going to repeat it once again. The statement of this question: a crystalline material has a set of a Bragg's planes separated by the 1.1 angstrom for a 2 electron volt newtons. What will be the highest order Bragg's reflection? Okay. Now we are going to solve this question. The given information of this question, given data is here. E, this is energy, and energy equal 2 electron volt. Okay. We know that 1 electron volt equal 1.6 into 10 inverse 19 joule. So we can write 2 into 1.6 into 10 to the minus 19 joule, and this is equal to 3.2 into 10 to the minus 19 joule. And D, this is interplaning space, and this is equal to 1.1 angstrom. So we know that 1 angstrom equal 10 to the minus 10 meter. So 1.1 angstrom equal 1.1 into 10 to the minus 10 meter. And particle is also Newton. So we know that the mass value of the Newton particle is 1.67 into 10 to the minus 27 kg, and H is Planck constant. H equals 6.62 into 10 to the minus 34 joule second, and lambda equal what, and n equal what. First of all, we are going to find out wavelength. Lambda equal h by under root of 2 me. This is the expression of de Broglie wavelength in terms of kinetic energy or energy. So when all the values substituted in this equation, then we will get lambda equal 0.202 angstrom. But we need to find out n equal what. Okay. So again, we can write from Bragg's equation 2d sin theta equal n lambda, and n equal 2d sin theta divided by lambda. When all the values substituted in this equation, then we can write n equal 10.89, and this is approximately equal to 10. Okay. Okay, our next problem is the statement of this problem. Thermal neutrons incident on sodium chloride crystal within bracket interatomic spacing 2.18 angstrom undergo first order diffraction from the principal Bragg's planes at an angle 20 degree. Find out the energy of the thermal neutrons. Okay. So the given information of this question. Solution. Interplaning spacing is 2.18 angstrom. So D equal 2.18 angstrom, and this is equal to 2.18 into 10 to the minus 10 meter, because we know that 1 angstrom equal 10 to the minus 10 meter. Okay. And glancing angle is also 20 degree. Theta equal 20 degree. Okay. And first order. So integer number n equal 1. Planck constant H equal 6.62 into 10 to the power minus 34 joule second, and 34 joule second. Okay. And particle is Newton. Particle is sodium chloride. particle is Newton. So Newton particle, mass of particle equal 1.67 into 10 to the power minus 27 kg. First of all, we are going to find out, we have from Bragg's equation 2d sin theta equal n lambda. First of all, we are going to find out lambda. Okay. So lambda equal 2d sin theta divided by n. Okay. And 2d sin theta, the 2 into d, the value of d equal 2.18 into 10 to the power minus 10 into sine 20 degree into sine 20 degree divided by n equal 1. After solving this part, we will get 1.922 into 10 to the power minus 10 meter, and this is equal to 1.922 angstrom, because we know that 1 angstrom equal 10 to the power minus 10 meter. Now we are going to find out energy. Again, we can apply de Broglie-Webb equation in terms of energy. Again, lambda equal h by under root of 2 me, both side squaring, lambda equal h square divided by 2 me. After cross multiplication, we can write E equal h square divided by 2m lambda square. Now we are put all the values in this equation. The value of h equals 6.62 into 10 to the power minus 34 whole square, and 2, the value of m equal 1.67 into 10 to the minus 27 into lambda, the value of lambda equal 1.922 into 10 to the minus 10. Okay, and lambda is square. After solving this part, we will get 0.0221 into 1.6 into 10 to the power minus 19. After solving something, you will get something. Say this is equal to dash energy. Okay. For your better understanding, I am going to repeat it once again. The statement of this question: thermal neutrons incident on sodium chloride crystal, interatomic spacing 2.18 angstrom, undergo first order diffraction from the principal Bragg's planes at an angle 20 degree. Find out the energy of the thermal neutrons. So the given information, interplaning space is 2.18 angstrom. So d interplaning spacing is denoted by d. So d equal 2.18 angstrom. And we know that 1 angstrom equal 10 to the minus 10 meter. So we can write 2.18 into 10 to the minus 10 meter. And theta is also glancing angle. So theta equal 20 degree. We can write theta equal 20 degree. And this is first order. So n equal 1. H is Planck constant. And m equal 1.67. Particle is, since particle is Newton particle, as we know that the mass of a Newton particle is m equal 1.67 into 10 to the minus 27 kg. Okay. So first of all, we are going to find out lambda with the help of Bragg's equation. 2d sin theta equal n lambda. So lambda equal 2d sin theta divided by n. When all the values substituted in this equation, then we will get 1.922 angstrom. And again, we can write lambda equal h by under root of 2 me. This is the expression of de Broglie wavelength in terms of the kinetic energy. So after squaring both sides, we can write lambda square equal h square divided by 2 me. Okay, and E equal h square divided by 2m lambda square. When all the values substituted in this equation, then you will get something. Okay, thank you. Our last numerical problem is the statement of this problem. A Newton beam of energy 0.04 electron volt is diffracted from the 100 plane of crystal. If the glancing angle for the first order maxima is 13 degree 10 minute, find the separation between two consecutive 100 planes of the crystal. Mass of the Newton 1.67 into 10 to the minus 27 kg, and also given sine 13 degree 10 minute is equal to 0.2273. Now we are going to solve this question. Solution: given particle is Newton, so mass of Newton equal 1.67 into 10 to the minus 27 kg. Okay, and glancing angle theta equal 13 degree 10 minute. Okay, and energy equal E equal 0.04 electron volt, and we know that electron volt is not SI unit of the energy, so it should be converted in SI system. So 0.04 into 1.6 into 10 to the power minus 19 joule. And also Planck constant H equals 6.62 into 10 to the power minus 34 joule second. Okay, joule second. Okay, and D equal what? Interplaning space. We need to find out D equal what. Okay, now we are going to, first of all, we are going to find out lambda. We have lambda equal H by under root of 2me. This is the expression of de Broglie wavelength in terms of energy. Remember this. Okay, now the value of H equal 6.62 into 10 to the power minus 34, and the value of 2 into m 1.67 into 10 to the power minus 27 into E. The value of E is equal to 0.04. Yes, 0.04 into 1.6 into 10 to the power minus 19. After solving this part, we will get, say suppose we will get, say something. Okay, again we can apply Bragg's equation. From Bragg's law, (2d sin theta equal n lambda and d equal n lambda divided by d sin theta. Okay, the value of n equal first order. Yes, value n equal 1. So n equal 1 and lambda, say this is 326 into 10 to the power minus 9 meter. So the value of lambda equal 1.326 into 10 to the power minus 9, and d, the value of d equal 2 sin theta. 2 into sin 13 degree 10 minute. Okay, again we can write 1 into 1.326 into 10 to the power minus 9, and 2 into sin 13 degree 10 minute is equal to 0.2273. Okay, 0.2273. After solving this part, we will get 3.14 into 10 to the power minus 10 meter, and this is equal to 3.14 angstrom, because we know that 10 to the minus 10 equal 1 angstrom. So this is interplaning space. Okay,